Thank you, Derek. It's a great pleasure to be here. I also met Derek in Madrid several years ago during the conference organized by Manuel Alcami and Fernando Martin. So Madrid is quite nice place to meetings. Yes. Okay. Today I will talk about small molecular animal, which is sodium rubidium molecule. This molecule is very famous in the cold physics and cold chemistry area. So in the first part I will talk about electronic structure and permanent transition dipole moments and various couplings, but today I will focus only on spin orbit couplings. And in the last part of my talk I will talk about exemplary processes occurring in this molecule. Okay, the motivation is that quantum control, the most important, or maybe not most, but the main aim of the quantum chemistry and molecular physics is quantum control of breaking and creating of the chemical bonds. And we are trying to do simulations in which we can show how it is possible using laser fields and playing with parameters of these laser fields to obtain the population, for example, in the deeply bound ground state, for example. Okay, so we calculated a lot of potential energy curves in the sodium, in the potassium rubidium molecule, including singlet, triplet, sigma plus, sigma minus, and pi and delta states. And we obtained quite reasonable results. Here you can see the, for example, mean absolute error for the dissociation energy, comparing with the existed experimental results. And here is the vibrational constant. So I think spectroscopic parameters are quite nice in this system. And here is the asymptotic behavior of our potentials. So also the mean absolute error is quite small in the comparison with the experimental results. Okay, so for this state we calculated also permanent dipole moments, which is important which will be important in our numerical experiments. Later we calculated also all-out transition dipole moment functions between many states. Finally we also calculated spin orbit all-out spin orbit couplings, and because we would like to see if using many potential energy curves and couplings and permanent transition dipole moments and also other types of couplings like radial couplings, like Elan couplings, something like this, if we will be able to describe in a reasonable way the time-dependent processes in this molecule. Okay, so what we are using? We are using quantum chemistry package, mainly MORPRO and spectroscopy, which is Python code developed in our group for raw vibrational calculations and the perturbation analysis. We are using effective core potentials, mainly large core potentials, and we carefully choose, augment, and optimize basis sets. Very often we have to calculate and optimize the spin orbit ECP parameters, because these parameters not exist in the in the basis in the basis. We are using to do this model optimization algorithms, for example, differential evolution, and also we are trying to use machine learning methods. Here today I will show you. I showed you results obtained by MRCI method, but of course we are using other quantum chemistry methods. Okay, so here is the example that we calculated and optimized the spin orbit ECP parameters for potassium atom. Because this parameters don't exist, so you can see in this table capital A and small a parameters, which leading us to obtain the spin orbit splitting, which is quite nice. The comparison of this is it's quite nice from the from the NIST database. Okay, so let's go to the time-dependent part of my talk. So we are solving the time-dependent Schrödinger equation, but rather system of coupled time-dependent Schrödinger equations. We've got two branches of our code. One code is based on is connected with the time-independent Hamiltonian, which is based on the famous Kozloff method, based on the Chebyshev polynomials. But I will skip this part because today I will talk. I will show you some simulations, numerical experiments, which was done using our C++ very fast code based on the based on the Schaffer and Kozloff method. This is semi-global method, which in which the each time step is corrected by several substeps in several substeps, which give us which allow us to obtain very high accuracy quantum dynamics calculations. So we investigated several experimental. We did several experimental numerical experiments because we would like to see what will happen if we transfer the population from the triplet sigma state to the excited state, and you can see that we are using here two atomic asymptotes. So our Hamiltonian is like this. So we are using 10 potential energy curves, permanent dipole moments, transition dipole moments, spin orbit couplings. The limitation of this approach is that we nowadays we are not using radial couplings because we are preparing this, and we are also started implemented the fully rotational Hamiltonian to have here any rotational couplings in the system. Okay, so we are using laser field in this shape. So here is the frequency of the laser field, the impulse center, intensity, and the time duration of our laser impulses. And here these are parameters of the two numerical experiment. I call it this pumping, because we transfer the population from the first triplet sigma state to the second triplet sigma state, and later and in other numerical experiment from the first triplet sigma state to the second triplet pi state, and the duration of this impulses you can see here. It is very worth to noting that we are using quite small intensities because we would like to decrease the influence of the permanent dipole moment in this numerical experiments, because if we use this kind of intensities, we've got the change of the potential energy curves is not exceed 10 wave numbers, and you can see that transition dipole moments from the in these two systems are quite large. So we obtained rather large population in the excited state, and you can see here that in the second triplet sigma state we've got 23%, and in the first triplet pi we've got 1.5% of the population. But the most important thing is that you can see here that due to the spin orbit coupling, the population is transferred also to the second sigma state and first sigma pi state, which are necessary to think about population transfer to the ground state, okay, of the molecule. And this scheme is quite promising because transition dipole moments from these two excited states are quite large. Okay, the second experiment is rather dissociative, but okay, we can transfer 75% of the population from the triplet sigma state to the second triplet pi state. But you can see that after 8 picoseconds the molecule starts dissociating. And you can see also this pink line that the quite large of the population is moved to the third singlet sigma state, and later to the second sigma pi state. But the transition dipole moments from these two states are really small. So finally, we did final part of this numerical experiment, and we optimized the impulses of the damping lasers, and we obtained quite small, but because this process is not efficient, so the population in the first singlet sigma state is not so large. Yes, and you can see that if we are using, for example, here is only two lasers. This is pumping laser. This is damping lasers. But if we will use more lasers, like laser pulse, laser trains, it will be possible to obtain to transfer more population to the ground state. Okay, so I am finishing. Sorry, Darek. To do quantum dynamic calculations, I think we have to have reasonable electronic structure with couplings, with transition and permanent dipole moments, and this is our group. From Gdańsk, Tymon is now in the Michał Tomza group at University of Warsaw, and this is acknowledgements, and thank you for your attention.
Thank you, Patryk. So there are our questions.
Thank you, Patryk. Nice talk. I was wondering, like, if you care about spin orbit couplings, why wouldn't you use a full electron basis? Why would you do ECPs?
Yeah, because in potassium and rubidium atoms, you've got plenty of electrons. Yeah, and yeah.
But it's still a small system. I mean, I would have gone full electron.
Yeah, we tried to do this, but the calculation, are much more demanding, and the accuracy was not so. The change in the accuracy was not so large. So we decided to construct the approach, because it is only one system, yeah, which I showed you. And we've got a lot of calculations for alkaline alkali diatomic molecules and triatomic molecules, and also alkaline earth molecules. So we decided to use large ECPs with carefully reoptimized parameters and basis sets and spin orbit parameters to have full approach which is consistent in the system. Yeah, I agree with you that it sometimes it is useful to do all electron calculations, especially to compare if you are not losing something. Yeah.
Okay, thank you.
So following this question, so how heavy are these calculations? Because you run it for like 10 picoseconds, right? And then you observe some transition at 2, 3, or 4.
10 picoseconds mean hours, or in the calculation time, yeah. But sometimes it is hours. Sometimes it is months. Yeah, if you would like to really see the because this is I showed you only 10 potential energy curves and couplings between them. We did calculations, preliminary calculations for all of the states. Yes, playing with some parameters, and we tried to create approach in which we will be able to really find the best way how to obtain the molecule in the deeply bound ground state, but it is nightmare in the case of the computational time. Yes, so 10 picoseconds it's small in the simulation, but in the computational time it's huge. Yeah.
Thank you.
So just a quick question.
Yep.
So you showed the vibrational constant for KRB, and it seemed extremely small, at about half a wave number.
No. I showed.
Is that like an excited state, or it's
No. It was
one of the earlier slides?
It was here. This is mean absolute error.
Oh,
For all states which we was able to compare with the experimental values.
thank you.
Okay.
So let's thanks again, Patryk, and all the speakers of the session.
Thank you.